What else? All right. So we know an orthogonal set is all the eigenvectors. All the vectors have a dot product of. Beautiful. And we can figure out whether or not things are orthogonal sets, right? So show that that is an orthogonal basis for R3. So we do work on that, yes. So is it orthogonal? Yeah, why? Because we did it last time. They're all orthogonal to each other. Good. So, but is it a basis for R3? Well, that's the one thing that we did not do. That I remember. How do we know that it's an orthogonal basis for R3? Right. They're linearly independent. And how do we show that they're linearly independent? There are no free variables, exactly. So when we mush these things into a matrix, and then, I mean, technically we could augment those things with 0, and then when we row reduce them, we get out 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So it's a basis for R3, in part because we have 3 pivots, right? If we just had 2 pivots, it would be a basis for R2, right? But they are linearly independent. Okay, so that's kind of showing that that is an orthogonal basis for R3. So we have an orthogonal basis. W is defined as an orthogonal basis. And so y dot u1. So we have all these weights. And so we're starting with y dotted with u1. And so what we have is, if I begin with y, and if I dot that with u1, what do we get out? What happens when I do that? What happens if I do that math? What do we get?
0.
Close. Right, so close. Close. Let's look at that math real quick. So if I, kind of distributed those vectors in. So again, these are orthogonal vectors. We have to kind of keep that in mind, and whatever, we could have had those same ones. We could still kind of define u1 as being that, and we could define u2 as being this. And then we have multiple, and that orthogonal basis goes on for however long you want them to go on, right? So if I do that, right, what I get is I get C1, so that's just a constant, obviously, and then U1 dotted with U1. So in that case, we don't get out 0, right? But in all the other cases, what do we know about U2 dotted with U1? We do get zeros, right? So that is going to melt away, and then we keep going, and we get CP, UP, U1, and all of these are going to be 0 because it's orthogonal, right? Are we good? So what do we know? So the only thing we need to find out what C1 is, right? And this is what we already did last class, I think, or the class before, I don't remember. Because I think last class was the test. So we have y dotted with u1 equals c1, u1. So that's going to be times, not dotted. It's a scalar. So what do we got on that? So let's do a little bit of math. How do we solve for? Right. Why can we do that? Why can we divide? But just remember from algebra 2, what can you never, ever, ever divide by? 0. And u1 dotted with u1 is not 0. We're not throwing in 0 vectors in there. Okay? So we know that C1 is going to be y dotted with u1 over u1 dotted with u1. Okay? Not here. And so therefore, what the heck do you think C2 is going to be? C2 is going to be what? Oh, replace u1 with u2, exactly. So y dotted with u2 over u2, u2, okay, and etc. Right? So we can find those constants if and only if we're talking about an orthogonal basis. Okay, if and only if we're talking about an orthogonal basis. And so what we did last class is, well, there is that formula, right? Whichever number you want. J is going from 1. J can be any number between 1 and p, inclusive, right? So we just replace those. So that is that theorem. But it has to be an orthogonal basis, and I'm saying that for lots of reasons. Okay? So express y as a linear combination of the orthogonal bases. And that is the exact same thing that we've been doing before. So some of you said that even if it weren't orthogonal, how do you express vectors, another vector is a linear combination of it? What are we going to do? Right. We're going to row reduce that. We're going to Jesus that, right? We could do that, right? And so if you augment it, actually, if I just took that and augmented it over here, we would get the values of C1, C2, and C3, right? And if you did that, so half the class could row reduce it, and the other half could do our new formula, since we're talking about an orthogonal basis. If you want to find out what C1 is, what did we just say? Okay? And so y dot u1 over u1 is going to be, right, 3 minus 7, right, because I'm slow, over 1 plus 1, right, which is negative 2. And I think we're good. That's going to be 3 minus 7, right? And so maybe it's easier. You don't have to worry about row reduction, right? If it's an orthogonal basis. Dividing dot products is a little bit easier than writing that thing if you don't have a calculator and things like that, right? Are we good? That's a whole lot easier. And so C1 is that, and we said that C2 is, so waving our hand at the rest is 5, and C3 is 4. So so what are we saying really? So it says to express y as a linear combination of the orthogonal bases. So how do we get from these vectors to this one right here? Yes. Yeah. Okay. So what we're saying is that y equals C1 times U1 plus C2 times U2 plus C3 times U3. And these are U1, U2, and U3. Right? That's it. Are we good? Yes, sir.
Are those J's?
Yeah.
What's
It's any number. So that J is really just saying that J is, so pick a number. 3, okay? So C3 is going to be y dotted with U3, U3, U3. So pick a number, right? And it's just saying that it's that if we're going to have 3, or we can have an orthogonal basis with 28 of them. And so 3 still exists. You pick a number between 1 and 28. Okay? That's it. So it's just the generic formula. So, and we can check that or not, right? And I think we checked that last class, right? Are we all good with that? And we can do that kind of in our head. So if I'm saying that negative 2 plus 5 is 3 plus 0 times 4. And then I'm going to take this C1 right here is negative 2, so that gives you 2 plus 5 times 2, 5 times 1. So 2 plus 5 is 7. So we got that, and then 4 is 0 plus 0 plus 4. So that works out. We express that as a linear combination, right? If those things aren't defined, you don't have to rewrite that, but you can, right? Just to double check it. So now we have orthogonal projections. I think this is where we left off last class. And I was going to start off with the warm up with that one, but we have this new thing that we're going to come back to a lot, and this is the new concept called y hat. Okay? Y hat. For any non-zero vector u, so we have this vector u, right? In Rn, so it's something that we can kind of graph or express as a vector. We want to write y as the following. So we have any multiple of u, so we can expand that, we can contract that, we can keep it the same. We have y as a multiple of a vector perpendicular to u. Okay, so here is u, and here is the vector that is perpendicular to u, right here, and it can go up, it can go down, right, whichever way. It's going to be actually going down. We're going to express it as vector is going to go onto that. Okay, so that's our new vector z, and that z is here, and that z is kind of there as well. Those two vectors are basically the same. It just has direction and magnitude, right? Are we good? So so we can solve for what z is. Y minus, we're going to use that y, that same y, whatever that y was before, 374, and then minus lambda times u. We're just talking about one vector in this case. So we're going to find out how much we're going to multiply by, whether I'm going to expand or contract that one, so it'll hit the other vector. Okay? So we're going to find out what that alpha is, what that thing is. So y hat is going to be that vector. That's the orthogonal projection. Okay? And so z is y minus y hat. So, and that's called the component of y orthogonal to u. Okay? So we're going to find out what that y hat is. We're going to solve for y hat. So we're going to compute the orthogonal projection, and I tried to graph that one, and it didn't really work out well for me. So we have that orthogonal projection of 1, -1. We have this vector. What are we calling this vector? Is that y or is that u? Yeah, this is going to be the y vector. So we're going to start off with that y vector. Onto the line through -1, +3. Okay, so we already know what y is. We're projecting that onto u. And we also have the origin. So what do we need to find? Yeah, we need to find z. And so we're going to be using a couple of, if I just want the orthogonal projection, what are we looking for? What is that orthogonal projection? Y hat, right? This is y hat. Okay? How do we find y hat? Yeah, we're going to find alpha, right? So y hat. So you're correct. So it's alpha times u, right? But what is alpha? Exactly. So alpha is y dot u over u dot u. Okay? So this is kind of almost exactly like finding C1, right? The same process. It's just that we don't have a base. We don't have a basis. We're just talking about two vectors. Okay? So what do we get? So y hat is y dot u over u. So what do we get on that? What is y dot u? What's the dot product of y and u? Right. -1 minus 3, or -4. Yes. Adam Kush. All right. And then what is u dot u? Oh, yeah. I thought that was like, I was looking for you over here. Like, you are here. I don't know what it says. I don't know if it says when convenient or immediately. It doesn't matter. What is u dot u? U dot u is what? 10. Student services is like on the back side, next to the clinic, yeah. Thank you. So 1 plus 9. Okay, so that will give us negative 2/5. Okay? Oh, sorry. And then I need to multiply that thing by u. So stick that in there. So y hat, it's just going to be 2/5, negative 1, positive 3. 2/5 of negative 1, positive 3. Is that correct? Is it negative 2/5? Okay, and it's whatever that number is. I mean, we can leave it like that. We're good? Yes? All right. So now we're going to write y as a sum of a vector in the span of u and a vector orthogonal to u. So we kind of already have this, really. So what we're saying, so we're saying that what we want to do is we want to have 2, 6. We want to write y as a sum of a vector in the span of u. So what's a vector that's in the span of u? And a vector orthogonal to u. So what do we need to find? How do we find a vector that's orthogonal to u? So there are lots of things that are going to be in the span of u, right? We got to figure out what it is. And so orthogonal to u is going to be what? How do we find a vector that's orthogonal to u? What are we finding? So what do we call that thing? What did we just call it in the last thing? Y hat. So a vector that's orthogonal to u is going to be y hat, right? Are we good? So what is y hat? What are we going to do on that one? How do we find y hat? It's very important that we know this one. What's our formula? Y dot u over. Okay. I probably should have gone back to that other one just to make sure that it's orthogonal, because that is important. So when we're done, we want to double check that. So y hat is going to be, what is y dot u going to be? I mean, we kind of know that, but what do we, y dot u is going to be what? What's on the top? 20? Over u dot u? 50? And then u is 7, 1. So y hat is going to be what? What is that going to be? Two-fifths of 7, 1. So what do we need to find? So actually, I did kind of lie to you, right? That's y hat. It's not, that wasn't the vector that's orthogonal to it, because we need to because that's not orthogonal to it, right? How do we find the vector that's orthogonal to it? And so what do we know about 2/5 of 7, 1? Is that a vector that's orthogonal to you? So I did lie when I wrote that up. Right. Huh? So is this y hat in the span of u? Yes. So I just misspoke on that one, right? So this is the vector that's in the span of u. Okay? So that's what y hat is. And I always have to double think about that, like double check that. Okay? That's a vector that's span of you. How do you find a vector that's orthogonal to you? So we have a vector that's in the span of you, which is 2/5, yes, of 7, 1. And a vector that's in orthogonal to you. So let's actually fix that. In the span of you, that's going to be y hat. And a vector that's orthogonal to you, like from the prior one, is going to be, what are we looking for? You said it, Daniel?
What?
You said, what is the vector that's orthogonal to you?
Z.
Z. So how do we find Z? Y minus y hat. Okay? So we have y hat. Okay? So what is y minus y hat? Well, y is 2/6. Not 2/6, but 2 then 6. Minus 2/5 of y hat, which is 7, 1. Okay? So what is 2 minus 14/5? Negative 4/5. That's the top number. And then the bottom number is 6 minus 2/5. 28 over 5. Okay? How can we quickly check that this is the vector that's orthogonal to you? Is the dot product equal to 0? Is the dot product equal to 0? Yes. And so you're right, and actually this is not that bad. That's negative 28/5 plus 28/5. You could also, if you don't want to deal with that, that's really the same vector as negative 4, positive 28. You don't need the fractions. All that does is change the length of it. It doesn't change it doesn't change the angle, right? It doesn't change the angle. So you can think about this as negative 4, positive 28, because they're both divisible by. They're both 4/5 and 28/5. Okay? So this is what Z is. That's the vector that's orthogonal to it. So vector in the span of you, this is the vector that's in the span of you, and the vector that's orthogonal to you is going to be negative 4/5 and 28/5. Okay, and we can still double check that gives us 2 and 6. But if we added and subtracted correctly, then we're going to be okay. All right? Well, we fixed one thing. So when we're finding y hat, that's the vector. Y hat is the vector that's in the span of you. And I think I know I said orthogonal to it, so I kind of messed that up. Okay? It's a multiple of u, so it can't be, or it's not going to be orthogonal to it. It's alpha times u, right? Or that constant times u. Okay? So the last one. So by the last one, it's the important one. And then we have another thing on that. So find the distance from y to the line through 0 and u. So we have this vector 3, 1, and we have 8, negative 4. I don't even know where that really represents. So how do you find the distance from y to the line through? How do you find the distance between two vectors? What do we need?
Do you even know the second vector? Don't you have to find the line from 0 to 0?
So we have 8, negative 4, and we have the line through 0 and u. There it is right there. There's 3, 1. So how do you compute the distance from y to that vector?
But that second one there is an 8 negative 4.
No. What do we need? The y hat. What is y hat?
Y multiplied with u times u over u times u.
Okay? So it's really saying, how is this thing being contracted? So what is y hat going to be?
Y dot part u.
Mm-hmm. So what do we get? Let's just go ahead and wave our hand to that math. Y dot u over u. Yes, it's going to be 2u, right? So y hat is going to be 2 times u, which is going to be 6, 2. So what does that tell us? How do we find the distance between? So what did we just do? We just contracted that, right? And now, how is that thing going to land on it? So what is the distance between those two things? There are 2 different ways to find that. So we need to go out to 6, 2.
Or can we just find z then?
Yeah, so how do you find z? Exactly. So z is going to be y minus y hat. And then we're going to find that distance. So what is y minus y hat going to be?
2 negative 6.
2 -6. Is that, so you can do it that way and that's beautiful, right? But what is that distance? Right, that magnitude. If we want to find distance, we want to find its magnitude. We want to find the magnitude of that z vector. Okay? So what is the magnitude of that, which is going to give you the square root of 40, which is obviously 4 plus 6 squared, negative 6 squared. Okay? Square root of 40. Leave it like that. It's obviously 2 square roots. Okay? So we're going to find out what is that distance? It's kind of the same thing as that first thing. We want to find distance between 2 vectors, right? You got to find that right angle, right? This is the vector that's orthogonal to that. Okay, we cut it off, and we're going from that vector to the other, down to that vector. The projection, right? We good? And so the last thing is one of the things that we're going to be doing a lot of. So we know what an orthogonal set is, right? What's an orthogonal set? All of them perpendicular, so therefore all the dot products are. So orthonormal is the exact same thing, but with one caveat. They have to be unit vectors, right? So none of those, so it's an orthonormal set if all of them are unit vectors. All of them have a magnitude of 1. So the first thing that must be true is they must be orthogonal. And so kind of obviously, are these orthogonal?
Yes.
So it has to be yes. So are they both unit vectors? Yes, they are. And then you can do that with fractions or decimals, right? So 0.36 plus 0.64 is 1. Square root. Okay? Same thing. 64 and 36. 4/5, 3/5, whatever. All right? Are they orthogonal? So that answer, orthogonal. Orthogonal. Are they orthogonal?
Yes.
Unit vectors. Which one is not? Second. Right? So, no, it's not orthonormal. Right? Because U2 has a magnitude of 1/9 plus 4/9 not equal to 1. I don't know what it is, but it's not 1. Okay? That's it. So unit vector. So I never do this math, but that math will come back later. Okay? Just be able to do it. So to have it technically, if we have vectors, suppose that is an orthonormal set. What's going to be if I have that vector? So we had that, what was it, 1/3, 2/3, and what was the other one that was a unit vector? What was that last number? And 2/3, right? That was, and then we had some negatives. I forgot which ones were negative, but it doesn't matter, right? So, and that 2/3 was up here. So this, what happens when I take actually the transpose of that? So this is, those actually would be vectors, but what happens when I take those and I do the transpose of all those things? So if I have a bunch, so I have this one, and actually we can do, what happens when I do the transpose? What will happen when I do that? If I have orthogonal vectors, orthonormal vectors, excuse me.
Can you use zero matrix?
We won't get the zero matrix. So actually so basically, that would be maybe U1. U2 is, I can't do that in my head. I can't do that in my head. So what happens when I do those? Let's actually work those out. What happens when I compute those? So I have U1 transpose, and I have U2 transpose, and I have U3 transpose. Make sure I'm writing this correctly. And those should be going down. So those are vectors still, but we transpose them. So which direction is U1 going? So I was actually kind of writing it not correctly, but they're going to be going across, right? Are we good? So this is going to have 3 components, right? The first value, the second value, and the third value. It's going to be going this way. And then I'm going to multiply that by U1, U2, and then U3. But those are 3 vectors that are going this direction, right? The transpose, they're going this direction. Okay? Are we good? Does that make sense? So U1 transpose times, so the first row times the first column gives you just U1 transpose times U1, right? But there are going to be components in there. That's going to be a dot product. Okay? And what do we get? What are we going to do right here? Well, U1 transpose, beautiful. Dotted with U2. Okay? And what do we get when and then over here is going to be U1 transpose dotted with U3. Or multiply. That should be multiplied. It's just, let's put parentheses around that. Okay? Because it's a 1 by 3 times a 3 by 1. Right? So it's going to give you just one value in each of those places. And then it's really just going to be the same thing. We're just going to copy U2, U2, U2 transpose, and then we have U1, U2, and U3. Right? So what happens, so I'll just say U1, U2, and U3, kind of stay right there. And then we have U3 transpose, U2 transpose, and U. Yeah, those should be U3s. Thank you. Transpose. So we know that if I take a vector, this is really like finding the dot product. That dot product is going to be 1. What else is going to be 1? Yes, so all the U2s and U3s. But what happens when I multiply? What is this value right here going to be? So it's exactly like finding the dot product. What's the dot product of U1 and U2 if they're orthonormal? 0, right? So everything else is going to be 0. And actually orthogonal. And so therefore the dot product is 0. So what happens when what is the resulting matrix going to be? The identity matrix, right? And it's identity because, why is that thing 1? Because what's so special about those vectors? They're unit vectors. They have a magnitude of 1, right? So just because they're orthogonal doesn't mean, So we have 2 vectors like 6 but they have the 0.6 and 0.8 vectors. Or I could have a 6 and an 8 vector. Those are not orthonormal. They are orthogonal, right? Because I can change any vector. I can factor out or multiply by 10. Multiply one of them by 10, keep the other one the same. They're still orthogonal, but they're no longer orthonormal. Does that make sense? Does that make sense? So I'm thinking about that negative 0.6 and the positive 0.8 and the positive 0.8 and the positive 0.6. So those 2 vectors are orthogonal and orthonormal. I'm not going to change. These are still orthogonal. If I change one or both of them to negative 6, positive 8, and I can change that to 80 and 60. That's still orthogonal, but definitely not orthonormal, right? Orthogonal, but not unit vector. Okay? No longer unit vectors. But I can take any vector that I want to that is orthogonal, and I can make it orthonormal, right? I can make them unit vectors. 3, 4, 1/5 of that, right? Are we good? So, and that's how we got the 0.6 and the 0.8. Negative and positive. So that's it. Orthonormal is what we're going to be talking about next time. So orthogonal matrix. So it has the identity matrix as you just said, and we're kind of done with the rest. We'll stop there. And those are, well, because that's it. Okay? So, yeah. Today is Tuesday. What on block is 30?